Now that we've fully constructed the real numbers, we will note some properties of the real numbers, as exemplified here in the theorem labeled 1.6. That is, for any real number a that is greater than 0, there's an integer n with the property that 1 over n is less than a is less than n. For any real numbers a less than b, there's a rational number r with the property that r is between a and b. To prove this, let's proceed by contradiction. First, if it is not true that there's an integer n1 such that n1 is greater than a, then n is less than or equal to a for all the integers n. So the subset n is as a subset of the real numbers is a non-empty set that is bounded above, and since we have a complete ordered field, the set n must have a least upper bound b. The real number b minus 1 is not an upper bound for the set n, so there's some integer n greater than b minus 1, but it is the case that n plus 1 is greater than b, so that b cannot be a upper bound of the set n, which is a contradiction. It follows that the assumption that there is not an integer n1 greater than a is false. Hence, there is a upper bound on any real number, or there's an upper bound on any real number, which we call n1 is greater than a. In particular, there's also an integer n2 is greater than 1 over a, namely because we've shown that there is a number n1 bigger than a. We simply let 1 over a be another real number, which is substituted into this a to generate the integer n2. By taking the reciprocals of these, we get that 0 is less than 1 over n2 is less than a. And if n is greater than n2, and n is greater than n2, if n is greater than n1 and n is greater than n2, then we have that 1 over n is less than a is less than n. If a is less than b, then what we've just shown, there's an integer n naught such that 1 over n naught is less than b minus a. That is, b minus a is a real number, so we've shown that there's always a rational number less than the difference, less than any real number. The set S is a subset of R of rational numbers, for which m over n naught for all m in the integers, for which m over n naught is less than or equal to a, has the upper bound of a. Hence, it has the least upper bound r in the real numbers. So, since r minus 1 over 2 n naught is not an upper bound of n, not an upper bound of s, there must be some rational m naught over n naught within s, which is bigger than that number, namely for which r minus 1 over 2 n naught is less than m naught over n naught. And we have that m naught over n naught is less than or equal to a, since m naught over n naught is within s, and a is an upper bound of s. On the other hand, we have that m naught plus 1 over n naught, which is going to be equal to m naught over n naught plus 1 over n naught, must be bigger than r plus 1 over 2 n naught, which is bigger than r, since r is an upper bound is the least upper bound of s. And consequently, we have that m naught plus 1 over n naught is not an s. So m naught plus 1 over n naught is bigger than a, which was our real number to start with. And we have that m naught plus 1 over n naught is less than or equal to a plus 1 over n naught, which is less than b. So we have that a is less than m naught plus 1 over n naught, which is less than b, which suffices to prove that there is a rational number between any two real numbers. In particular, in applying this, we note that for any real number r for which r is greater than 0, there are integers n within the integers, such that n is bigger than r and 1 over n is less than r. And any ordered field which obeys this property is called an Archimedean field. Sometimes we call Theorem 1.6 the Archimedean property, and we use it to define certain objects. Furthermore, for any two real numbers, r1 and r2, there are rational numbers p over q, such that r1 is less than p over q is less than r2. So any real number can be approximated as closely as desired by rational numbers. On the other hand, the field R as defined axiomatically is complete, in that, for as an example, any positive real number has a unique positive square root. We will now demonstrate this. Let's choose any real number R for which R is greater than 0 and introduce two sets of numbers. The set X will denote all those real elements such that X is greater than 0 and X squared is less than R, and the set of Y, which is all those elements, little y, which are positive and are, when you square them, they're bigger than R. These sets are clearly non-empty, and we have that X is less than Y for any X in X and Y in Y. So we can apply the completeness of the real numbers, since X and Y are given to be real numbers. So there are real numbers x naught and y naught, for which x naught is the supremum of x, and y naught is the infimum of y. Any y serves as an upper bound for x, so it must be greater than the least upper bound of x, and thus x naught is less than y for all y. And x naught, we will note, is a lower bound for y, so it must be less than the greatest upper bound, the greatest lower bound of y, and thus x naught is less than or equal to y naught. If we have the x naught squared as less than r, then x naught squared we can write as r minus epsilon for some positive epsilon. And if a is, which we'll write as 2x naught plus 1, and h is a real number for which 0 is less than or h is less than the minimum of 1 or epsilon over a, then we have that 2, by plugging in a, we have, by plugging in a and applying our definitions, we have that 2x naught h plus h squared is less than 2x naught plus 1 times h, which is ah. So we have that if you square this, we get 2x naught plus h quantity squared is going to be less than r minus epsilon plus ah, which must be less than r. Thus, x naught plus h must be an x, which is going to be a contradiction since we chose x naught to be the supreme of x. And consequently, we have that, then we would have that x naught squared is bigger than r. On the other hand, if we consider the set of upper bounds y, then we have that if y naught squared is bigger than r, then y naught squared can be written as r plus epsilon for some positive epsilon. And if we write h as the minimum of y naught and epsilon over 2 y naught, then y naught minus h quantity squared is going to be y naught squared minus 2 y naught h plus h squared, which can be bigger than r plus epsilon minus 2 y naught h, which can be bigger than r. Thus we have that y naught minus h is within y, which is a contradiction because we had that y naught was the infimum of y, and therefore it must be the case that y naught squared is less than r. Consequently, altogether we have that r is going to be less than or equal to x naught squared, which must be less than or equal to y naught squared, which is going to be less than or equal to r. So since we have bounding in both directions, we have that x naught squared is equal to y naught squared, which is going to be equal to r. This uniqueness is pretty clear, as you can check that the square root is uniquely defined. With that, we've completed the second section of the algebraic fundamentals, and namely we've discussed groups, rings, and fields. And next we'll continue with algebraic fundamentals found within linear algebra in chapter 1.3. I encourage you to, if you're confused at all in the next chapter, to go and study my course on Sheldon Axler's Linear Algebra Done Right, because that book is very informative and can help clarify a lot of the ideas that are brushed over in our next brief overview of the field of linear algebra. Thank you.